Okay. Well, thank you everyone for joining the Corundum developer meeting today. Okay, so first off, I got a couple of slides here for status updates. Let's see here. The agenda. I got some status updates, and then we're going to hear from Adam John on the 10G and 25G switching that he's been working on. All right, so let's see what's new. So over the past few days, I've been starting to put together some documentation for Corundum now that a few pieces are starting to look a little bit more finalized. Um, most of this other stuff is still kind of carryover to-dos. The main things that have had some progress are the DTY and PLL Drp interface integration that I've been working on, as well as some of the stuff that can be done with that. And the 10G 25G switching that Adam John is going to talk a little bit about. And then something that came up pretty recently is the JTAG to the application section. I've done a little bit of work on that. The idea being to facilitate the debugging and use of soft cores inside of the design. So it's specifically inside of the application section, but this can be used to debug board level stuff as well potentially. Right. So for documentation, I'm setting up Sphinx. So it's used by Linux kernel, Cocoa TV, whatnot. Seems like a pretty standard framework to use. I know the folks at Missing Link Electronics have been using this as well. So currently, I've imported a bunch of content from the README and the wiki on the repository, and I've put together a bunch of documentation for the register blocks. So I guess I can show that real quick. I have some of that. Let's see. Just the stuff that I've been working on here. Don't quite have all the details sorted out, but started to get this put together. So we've got the overall top level documentation, and then if we go down into the FPGA, so we can actually import figures and whatnot properly. I've got the documentation for the register blocks. So these are what are used inside of the register space in Corundum. They are, it's something that's you can enumerate to figure out, what components are present, and then each one of these will have a little header attached, and then following the header, there's going to be other fields for, either informational fields or control registers. So kind of similar to the PCI Express configuration space. So, for example, you got the firmware ID register block, which has, a bunch of ID related stuff. So previously, this was just kind of defined in the code and either in the Verilog and in the C code and whatnot, but I've been transferring it all over into Sphinx. So we can take a look at that. And the cool thing about Sphinx is you can generate not only HTML documentation, but also PDF. So we have, PDF documentation. It looks like this. So this uses LaTeX. So haven't gotten all of the details figured out yet. I think there's still a few oddball formatting issues, but for the most part, it's starting to look pretty good at this point. So hopefully I'll be able to get that up in the repository within the next week or two, and then we can start iterating on that. And as new features get added, we can document as we go, basically. Yeah. So one thing with the documentation is I don't want to bother writing documentation for old stuff that's going to be outmoded and replaced. So now that we have it in place, we'll start with the register blocks, which are, at this point, I have most of those documented, and then start working on the internal components. So, yeah, that's that. Let's see. So moving on to some of the PHY layers stuff. One of the things that I've been looking at is the adding some control and status registers for the PHYs. And the idea behind this is we can, from the register block, we can see what the capabilities of the PHYs are, because we can have, feature bits for that. And then we can also see some link status information. We can see the current speed if multiple speeds are supported, and, check auto negotiation status, although I don't think right now there's not much in terms of auto negotiation supported on most of the designs, but this will at least provide a pathway for that sort of thing. And then it'll also permit the driver to control things. So if we want to flip between 10G and 25G, we'll have bits in these registers to support that sort of thing. So still trying to get these registers figured out in terms of exactly what we need in there and whatnot in a way that's, well, we hopefully don't have to rewrite it multiple times in order to get all of the features that we need. But we'll see. With the version registers, if that's what we need to do, then that's what we need to do. All right, so that's one thing. And then the next piece is the DRP interfaces to the actual transceivers. So this is more of a Xilinx thing. For other FPGAs, you should have a similar kind of register-based interface to the high-speed transceivers. So the main idea behind this is it will provide access to the configuration space on the transceivers, and then you can run various diagnostic operations. Now, one thing that I've been trying to do is keep all of the drivers or all of the device specific code out of the driver, such that you don't need to port that across the main driver and the DPDK driver and whatever. Only the user space tools will have device specific code. So for things like changing the link rate, that will be done through some other interface that can be standardized. And potentially that's going to be, talking to a soft core or something like that. Right. So for the DRP interfaces, I need to make a kind of a bridge module that connects these to the NIC register space so you can poke at it. And then I also need to implement a few reset lines and a couple of other things that can be controlled from this register space. So the status of this is I'm working on it. Still have a few more kinks to work out, but what I did do is get the iScan operational using this other framework that I put together called the XFCP. So I did this to just make sure I had all of the algorithms worked out correctly, and I know exactly what signals need to be, I need control over, and what registers I need to poke at in what order. So this little eye diagram plot that I have here is just a simple measurement from a VC108 board running at 25G. So the GTY transceivers on that device. And the Xilinx documentation says that, hey, you can run the iScan on production traffic without disrupting it, and you don't need anything other than DRP access. But well, that's wrong, because you need to flip a couple of reset lines in order to set it up. So and if you're going to reset stuff, then well, it doesn't work so well for application traffic, because you're kind of going to be disrupting things a little bit by resetting the transceiver. But anyway, I did manage to get it working. And Intel has their own version of this same sort of capability called ODI, for on-die instrumentation. For those of you not familiar with iScan, the way it works basically is the transceivers have an additional sampler, and then you can offset that sampler in voltage and in time. And basically what the logic does is it compares the main sampler to this extra sampler, and it sees if they disagree. And if they disagree, then it counts that as a bit error, basically. So what you do is you plot this bit error rate offset by different voltages and different times, and you can get an idea of how much margin you have both horizontally in time and vertically in voltage at the receiver. So pretty useful capability, because this gives you a view essentially after the equalizer inside of the FPGA, which is almost impossible to probe otherwise. And it also means that you can get an idea about the link quality without having to figure out how to probe, the BGA balls on the chip from an oscilloscope or something like that. Anyway, so progress is being made there. Now that I have this working, once I get the connection working to the main NIC address space, then what I need to do is port this support over to a user space application so that you can run this against Corundum. Because right now this only works in Python with this other interface protocol that I have. All right. So the next thing is 10G 25G switching. This is something that I've had on the to-do list for a while. The idea is to be able to switch between 10G and 25G link rates on a per port basis, at runtime. So instead of having to rebuild the design, you can just go in with eTool or something and flip some bits, and now you're running different links at different rates. And the idea is that I'm going to take this and add it to all of the 25 gig designs. So we'll have for everything that supports 10 gig, we'll have a 10 gig design. For everything that supports 25 gig, we'll have a 10G, 25G switchable design, and then we'll have all the 100 gig designs. So for boards that that can support that. And potentially this will also be extended with the ability to change some equalizer settings, DFE versus LPM, which in certain circumstances you'll want to use, one over the other. But yeah, so previously Adam John asked about transceivers. So I asked if he wanted to work on this, and I guess he's been working on it over the past couple of months or something like that. So after these status updates, then we'll get a little update from Adam John over what he's been able to accomplish in terms of getting the GTY transceivers to switch between different link rates. Now, before we can integrate this into Corundum, there's a few things that need to be done. Namely, because we have to reset the transmit side as well as the receive side, we need to update the transmit engine components to handle drop transmit packets. Because right now, if you reset it at the wrong time, it'll cause the whole design to hang, which is not great. And the other thing that we need to do is get the PHY control registers implemented, so we actually have a way of controlling the link rate, or we have a way from the driver to control the link rate. All right. So that's 10G 25D switching, and then recently what's come up as well is how do we debug soft cores running on Corundum? So RISC-V or something else. And there's a few different possibilities for this. Kind of the initial thought is, well, these cores tend to have debug interfaces, and it's not all of them, but some of them provide a memory mapped version of it. But then the question becomes, if you want to have multiple cores, how do you map that into the control register space, and how much space do you have to set aside, yada, yada, yada. It's unclear, if there's a clean way of doing that. But a lot of these cores support JTAG, and the great thing about JTAG is you can just easily put a bunch of different components on a JTAG chain. So if you do that, then what we can do is provide some standard registers for speaking to this JTAG chain. We can thread the chain all the way into the application section, and then you can attach as many soft cores as you like inside the application section, and then debug them using standard tools. So the question is, how do you actually make that connection back to the host? So one thing I've already gone ahead and done is added the JTAG signal pass-through from kind of the top level of the design all the way down into the application section. That's just a matter of, adding some input and output ports and making sure they're properly connected. But the next step is to actually connect at the top level or in one of the core modules, connect this JTAG chain somehow to the host. Now, the simplest way to do this is just to bring it out on IO pins, but not all FPGA boards are going to be able to do that. A lot of the PCIe form factor ones don't really have any additional, GPIO anywhere. So that doesn't really work. And you need an additional JTAG adapter. Another option is the Xilinx virtual cable over PCIe. And the idea with that is they have a PCI Express extended capability. And then you can talk to that from user space. And OpenOCD can actually talk to that natively, which is kind of interesting. So that's potentially a really good short-term solution because OpenOCD can talk to it. The Xilinx tools, I think, can talk to it. Certainly hope if it's a Xilinx virtual cable that the Xilinx tool should be able to talk to it. But it is somewhat dependent on Xilinx devices because of how it interfaces with the PCI Express IP core. So you're not going to be able to implement that on all devices. I think you could probably implement it on at least some Intel devices, but it's a totally different interface to the PCIe IP core. So you would have to basically rewrite that block. And yeah, it's a good short-term solution to get stuff up and running, but in terms of, something that's vendor independent long-term, maybe we need a slightly different approach. Another potential idea is B-scan to JTAG. So the idea is to bridge the FPGA's own JTAG chain to this internal chain. This could also be potentially a good short-term solution because it's pretty simple to implement. But it does have downsides as well because this is controlled, not over PCIe, but over, USB or, some other external JTAG. So for something like an Alveo board, you'd have to have a USB cable plugged in order to use this. Or for like an Alveo U50, you have to have the Xilinx proprietary, whatever it's called, Alveo debug box thing in order to take advantage of that. You can't just do it over PCI Express. So, and then also Bscan is a Xilinx specific component. So this only works on Xilinx devices, although I think there are probably equivalent techniques that can be used on other FPGAs. So ultimately, the long-term solution is to basically put together a customized register block that sits in the PCI Express register space, and then have some customized software to talk to that. And the trick with that is coming up with a standard protocol between that software and then standard debug tools, because things like OpenOCD mainly just want to talk to USB devices. They don't want to talk to other pieces of software. So what we may need to do is implement like the XVC TCP protocol in OpenOCD, and then implement that protocol in our own little program which can talk to the register block. So this is starting to become a little Rube Goldberg-esque, but I think it's going to end up being the most flexible solution. So in this case, if you wanted to debug a software, you have GDB talking to OpenOCD, which would be talking to a Corundum specific program, which would then be poking at the PCIe register space. And then that would talk to the JTAG chain, which would interface with the debug modules on the cores. So lots of components involved, but this should work on any device as opposed to be limited to just Xilinx devices. So anyway, getting back to the status for this, the JTAG pass-through signals have been added, and the interface is currently to do. I know Leon has been spending some time working on this and actually has a couple of things working. So potentially he'll be able to join us at some point and give us an overview of what he's been able to accomplish. Because I think he got the XVC PCIe support operational. So yeah, let's see, what else do I have here? All right, so I've been putting up the slide a few times. It's kind of the to-do list for the stable release. We haven't checked off any more of these in a while, but making good progress, right? We still got to get variable length descriptor support and the on FPGA management software operational, as well as some tweaking of the ingress and egress pipelines. But yeah, oh, and then also, I guess I could add one on here for documentation. If we can get documentation on most of the pieces, I think that would also be a good thing before we can start cutting stable releases. But yeah, making progress on that front. Okay, so at this point, we can turn it over to Adam John to talk about the 10G and 25G switching that he's been working on. All right, Adam John, are you ready to present?
Sure, I'm ready.
Right, let me stop this and then you can take over from here.
I will try.
I may need to push a button here. Okay, there we go. You should be able to present now.
Can you see my screen now?
Yeah.
Okay. Hello, everyone. For those of you who might not know me, I'm Adam John Skro, and I work for a Turkish trading HFT and telecom-based company called Bull Technology, or Bulltech in short. And today I'm going to update you with coming 5-layer features and explain some of the topics here. First of all, I want to introduce you for those who who is not familiar with that, some terminology, and after that I will explain the goals and what the progress. And GTY is, as you might know, it's a transceiver provided by Xilinx, and it's present in UltraScale and UltraScale Plus, and it has channels and commands. I will show this in upcoming slides, and 4 channels combined have a common QPLL block, which contains 2 QPLLs, which are more powerful than these channel PLLs that are present in at each channel. So in our in our case, we want to use this QPLL0 and QPLL1 for 10G and 25G switching. So if it's required that some of the channels are working at 25G and some of them are working at 10G, both QPLLs will be on. I will explain later. But and we have a DRP interface Alex told about. It's very simple interface. You can just enable the signal and provide the address to read data, or you can provide address and data and write to some registers inside each channel and command. They have independent interface, each of them have. Of course, the first goal is 10G, 25G switching. And after that, we want to independently turn on or off each channel or PLL. And we want to configure TX configurable driver and RX equalizers. And we want to do margin analysis. Alex has done some of that, as he told us. If I'm wrong, can you correct me? I would be happy. And if you have questions, I can answer while talking. And Alex's idea was that we want to have 25G and 10G working on the same quad. As you know, for FPGA boards, they might have one QSFP 28 for one quad. So we might have breakout cables, or we might have single SFP plus or SFP 28 connectors. But the idea is that each channel should have independent 10G, 25G switching. For that to be possible, we need to use both QPLLs. So if we use single QPLL, then when we try to change this one, for example, we should change all of them. So we need to use both QPLLs. One will be working at 25G, one is used for 10G. And so to do that, we had to change this RX programmable divider attributes, and also the same thing for TX side, and select one of them, whichever use. So you can select.
Why would you need to change the programmable divider?
So because we are using this in 64-bit asynchronous gearbox case.
Right, but you should have the same divider setting for both 10G and 25G, right?
Really? I checked this and there was some change. I don't know, so I changed.
Okay. Yeah, all right.
There
so
was
it's possible.
Difference.
Okay,
yes,
yeah, it's possible that there's some oddball settings.
There were a lot of tons of
okay.
other attributes that were changed, but it doesn't tell about what they are on documentation. But when you generate with 25G and 10G separately, there are some differences in between. So for completeness, I changed them all.
Okay, yeah, because the programmable divider is going to be configured for the same division factor, but there could be some other oddball parameters that need to be changed.
Yes.
I have no idea what needs to be changed, but yeah, there's various tuning things, I guess. Interesting. Okay.
And after that, there were a lot of changes, but these aren't the main ones. This is actually the main one. This is not important because we are not using the output of this. But for completeness, I changed these two. I don't know if it's a good idea or not, but do you think it should be changed or not? Because we are using this one, not this one.
I mean, if we're not using that output, it probably doesn't need to be touched, but maybe we can use this capability to switch between other protocols later that maybe need that. I don't know.
But I changed this one to for completeness. So I don't know if it's required, but I changed this too and did the same thing for TX side also. So the second capability is to be able to turn on and off each channel. For example, if we are not using this channel, we can turn off. Or if all of them are working at 25G, then we can turn off this QPLL. Or if all of them are working at 10G, we can turn off the other QPLL. I somehow started this. By the way, this one is working on example design. I used two different transceivers, and I connect a cable from one, for example, from here to here. So I am using, so I don't have so many resources to be able to test with two FPGAs, but I connect these two interfaces, and it was working in that case. So when I change to 25G, it goes to 25. When I change to 10G, it goes to 10. So I will have to do this, and I think this does not take so much time because reset is required here as well. But here we need to reset QPLLs as well. But here we are not resetting QPLLs, obviously, because we are not changing them. We are just resetting channels. So after that, after finishing this, I will integrate the Corundum and will try to upload that. So the main thing that I need to do in upcoming days and weeks is doing this and combining these two and integrating to Corundum. These are, I think this should be next step, maybe. This is, we have configurable TX drivers, so we can change differential voltage swing and precursor, post-cursor transmit pre-phases. So we can have different configurations, and on the RX side, also we have different equalizers. So Xilinx has a low power mode. So I'm talking about Xilinx, by the way. So of course, this should be done for Intel device too, I think, right? And we have decision feedback equalizer. So the schematic is slightly different, but the same logic. So we can configure or choose between equalizers. And by configuring this and this, we can analyze eye diagram done by Alex, and of course by offsetting the different places and measuring the bit error rate, and maybe it will be useful. For example, if it's working on harsh conditions on data plane, maybe one can configure this and try to do his best or to get better eye diagram, or there might be eye metrics and the user can automate it so that the application tries to configure this and tries to get the best eye diagram possible, or maybe something like this. I'm not sure for that. So completing that 10G 25G switching makes it more flexible, as you know. And this things makes this Corundum work at more harsh environment. So if you have questions, you can ask me. Thank you for listening. You can ask questions if you have. Does someone have?
Yeah, maybe I do the head start. So thank you very much for your work. Just one question is about why do you want to actually switch off unused QPLLs? So I guess it's very little amount of power you will save.
Okay, I'm not sure about the amount of power that can be saved. I haven't checked that, but each channel has power down signal input, so you can make it. So that is actually used by PCI Express, but there are four main power states. But when you use, in our case, we use, for example, there is 2-bit signal. So if we make both high, this will be powered down, or any one of them. Each of them has its own power down signal. QPLRs also have power down signals. Of course, after turning on, we will have to reset. If it's channel, we'll have to reset that channel. If it's QPLR, first of all, we power down any QPLR if we are not using that. So after this lux, then we can use this, we can switch one of the channels to use this QPLL and reset the channel and do, I think we'll do this way. But maybe there will be something problem. We cannot know the future, but I think this will work.
Well, it should work, but there is a lot of hassle known with powering transceivers up and down during runtime. So,
well, I mean, we'll see about that. I think that the main thing is to turn off the unused QPLL. But I mean, if it doesn't work, then it doesn't work. So
yes,
that's kind of the idea. We'll try it. If it ends up being a big problem, then we don't have to necessarily take advantage of that. So
yeah, and I guess that's what I wanted to get on the point. So maybe focus on the other functional aspects rather than trying to save, I don't know, 0.5 milliwatt on PLL power.
I think it's a lot more than 0.5 milliwatt, but yeah, that's a good point.
Yes, but not compared with whatever else the FPGA does.
Hey, Alex, can I give you some observations?
Sure.
So we've been using DRPs for over 10 years on multiple FPGA platforms. And the way we do it is we use Axie4 Lite for the abstraction. And there's several reasons for that. One of which is across different platforms. For example, on Intel and Microchip, the TX-PLL is actually a separate block and uses a separate DRP interface to get to it. It actually gets even more complicated on Microchip because on their devices, there's only one DRP interface. You have to bring up, and it's a real pain on switches because you have to bring up all these DRP interfaces up to this one central services hardware block they have. The other thing is you want to make this as flexible as possible. You know, you're only beginning to run into the pain and suffering you're going to run into dealing with PLLs. We've had a lot of issues. There's all these little rules that aren't published and sometimes aren't fully known when they first roll out these devices, particularly in terms of things like crosstalk between blocks, jitter performance, particularly with respect to difference ref clocks. So these multiply divide ratios on PLLs some work better than others, even though they give you the same numbers in terms of jitter performance. The other thing with equalization, if you're going to do KR, and RapidIO has something equivalent to KR, you know, it's adaptive equalization across the link, you're going to need to have a processor in the loop. And we're actually using RISC-V for that, small RISC-V course. Or you can use the host if you've got a processor in it. You need as much flexibility as possible because the way these guys map these CSRs for handling these, you know, incrementing a tap is all over the map. And on older Xilinx devices, just to change one of these parameters, you had to do multiple read, modify, write cycles because they spread the bits across multiple CSRs to save address decoding. Ugh. So I guess my only message is you want to have as much flexibility as possible. And I would just slam everything behind an Axie4 Lite interface and make that your abstraction. Because they all have different hardware interfaces. Mapping them to Axie4 Lite is pretty easy. As a matter of fact, on the most recent versions of the transceiver wrappers for Versal, they actually provide you with the option of automatically generating an Axie4 Lite wrapper. So anyway, that's my take on it. Keep it flexible, keep it simple, just abstract everything beforehand to Axie4 Lite and make it software after that.
Yeah, those are definitely some good thoughts. I'm definitely going to be mapping these into something else. My thought is instead of sending it directly to AXI4, so it's you have basically a memory mapped block, basically just providing, you know, address, data, command registers. So you write the DRP address and data that you want, and then you poke the command register to actually perform the operation. The idea being that DRP is kind of a crappy protocol, and that you can't really tell if there's an operation currently active. So what you can do is keep track of that with this little interface block, and then if the design gets reset, it doesn't screw up the DRP interface and vice versa. Versus if you use something like AXI Lite and you reset the control side, then you might end up needing to reset the entire FPGA to get out of that.
All of that can be abstracted through Axie4 Lite, but okay.
Right. Well, I guess, okay, so I guess it's a difference between, you know, whether AXI4 Lite is directly connected, like you have a big portion of address space that gets turned into DRP registers versus if you have some intermediate registers. So that's, so yeah, my idea is that instead of memory mapping a huge block of address space that then corresponds to the entire DRP address space, we just have a couple of registers that you access via AXI4 or a similar protocol that then end up generating the DRP operations on the other side. Instead of interfacing directly with DRP.
Okay. So for example, if in the case where you've got things split between CSR locations, you're going to build all that into a state machine?
No, I mean, you would be accessing stuff indirectly, right? It's the difference between if I want to talk to register, you know, number 5, I make a, you know, an AXI operation to register 5. That would be the direct way of doing it. The indirect way of doing it is I write 5 to this register, and then I write my data to this other register, and then I poke a control bit that actually performs the operation. And then, you know, so it's a little bit more complicated, but you're using less address space in the NIC control space and whatnot. So
Really care about address space? I mean, we have 256 port controllers, and we just do bank mapping. So, for example, all of our, we have a megabyte for the DRP space, and we've never run into anything that needs that much address space, and we just bank map that into a port select. The maintenance space in RapidIO is 24 bits, so it's 16 megabytes. So, you know, I'm not sure where the concern about address bits are relatively cheap, but okay.
Yeah, I don't know. I guess potentially that we can rethink that, but we'll start with the initial implementation here and see how things work out.
Okay.
But thanks for your comments. This is definitely something that we're getting up to speed on.
So
Yeah,
maybe
and
an
also the
additional,
other thing about the DRP interfaces is it looks like that they're trying to maintain backwards compatibility. Like I was looking at GTH and GTY, and a lot of the registers are the same, even though for GTY they add a whole bunch, so they end up being in a totally different spot. It's kind of weird. Anyway, Ulrich, you wanted to say something?
Yeah, I just really wanted to second what Ken said, and so transceivers tend to be like halfly officially publicly documented, and the behavior is, I don't know, you will find very weird behavior, and especially with resets and these DFE settings, for example. So yeah, I just want to say second this. This is really interesting what happens there, and where the knowledge is actually accessible.
Yeah, I mean, the more you make the state space flat and totally naked and exposed to your software, the lower the probability you're going to get hosed and wind up having to crank a bunch of state machines. I mean, that's just memory map it, make it really brainlessly simple. Because one of the problems with like Xilinx, for example, they sort of figure, well, we own this, we can change it anytime we feel like. And believe me, Xilinx has the best documentation for transceivers.
I agree with you on that.
The other
having
guys,
looked at the Intel documentation.
Oh, wait until you see the microchip stuff. But you're probably going to have to deal with microchip, and because a lot of these guys like Lattice and microchip, because Intel and Xilinx have sort of abandoned the mid to low end FPGA market as they go after the data center, Lattice and microchip are getting a lot of traction, particularly within the context of you can't get Intel parts. So we spend half our time over the last 6 months helping people port from Intel parts to microchip and Lattice. And their documentation and their transceiver simulation models are really rough and ready. But anyway, I mean, you guys are doing something specific for more sort of a data center market, so maybe you don't care, but that's our experience. So
that is a useful thought. Yeah, I guess the deal with those guys is not so much they make good parts, they make reasonably priced parts. So if you have to deal with the crappy documentation or whatever, that just kind of comes along with the territory.
Yeah, and even these low-end parts from Lattice and Microsemi have 10 gig transceivers, and they're all coming out with 25 gig transceivers real soon. So people trying to do these things are going to be looking at these parts.
Interesting.
Particularly as you look at like these high-end FPGAs. I mean, Versal's a great part, but they're really expensive. So if you're just looking at a NIC, because we were looking at that for doing a CXL NIC bridge to Rapid I/O, and all the Intel parts that have CXL interfaces on them are these big honking data center accelerators that are just way too big to build a bridge. That type of thing. So the macroeconomic things going on in the market is driving a lot of this. Anyway, end of rant.
Okay. Yeah, I mean, that it might make sense to look into some of those microchip parts just in terms of having something that's a little bit more affordable for people that don't necessarily need the ability to run custom application logic on here. I know there's definitely been people that have been asking me here and there about, hey, can I just run this on a $50 FPGA board? I mean, it's like, well, I think most of the parts available at that price point just don't have the capabilities, but that could be changing. So I
Yeah,
didn't
just to
realize they
put
were
in
coming out with 10 and 25 gig transceivers on those things. That definitely opens up some potentially interesting doors.
Yeah, so just take a look at, there's a board with a micro semi polar fire part on it. It's got 10 gig transceivers. It's got an SFP plus on it. And it's called the Everest kit. And it's like $600 for an FPGA development board with 10 gig transceivers and a PCI Express interface. So the only reason I'm harping on the cheap part is we do a lot of work with universities. Like we're located in Corvallis and we work with Oregon State University. And, you know, their budget for development boards is, you know, please give it to us free. So lower cost development boards for students is a big deal.
Gotcha.
So this Everest board actually works pretty fine. So we use it also in at least 2 projects now, and build another board kind of as a fork. But from a PCI Express side, I guess it doesn't really match what Corundum requires to make it work.
Yeah, so that's the one thing that I've always been concerned about with these some of these boards. In fact, I think I even looked just briefly at the documentation for a couple of the microsemi parts, and yeah, for Corundum, you know, since we have our own DMA engine, it doesn't necessarily work with some of these parts that have hardened DMA engines on them. Right, if it's, you know, hardened PCI Express, that's good, but if it's hardened PCI Express and DMA, then that could end up being a problem. So
right, that'll be a boat anchor.
Yeah.
Although it's not pretty obvious if this is, if the DMA part is also completely hardened, or if there is any additional way to access streaming TLP data. It's just not, there is no IP core providing this interface.
Right. Well, one thing I will say is that even if we can't get TLP data, it's not necessarily a deal breaker, right? Because what you could potentially do is write a, you know, swap out the DMA interface module again for something else, right? You could do, so for example, it might be possible to take Corundum and run it inside of like the Xilinx AXI DMA bridge IP, right? If you take Corundum with the AXI interface, and then you bridge that, that might be possible. It's just a question of, you know, how much of that DMA IP core can you bypass, right? If it has a bunch of control registers that are eating up one of the bars you can't bypass, then that's a problem, right? So part of it is, you know, being able to get control over that. The other part is, you know, being able to implement all the bars. So for Corundum, we need full control over the bar space. So if they have bar 0 that's dedicated to their DMA IP, then yeah, making that work with Corundum is not going to be so great because you're going to have to do some extensive driver modifications and whatnot. So I don't know. Anyway, something to think about, but problem for a different day.
Yeah.
All right, let's see. So is there anything else to discuss here? Anyone else have any questions, comments?
Maybe just a quick mention. So today we provided an update on the Sync SoC integration path, and we finally tracked down the root cause for the platform to hang. And I guess it's something we did talk about 2 months ago.
Right.
So it's really coming down to
it seems to be some sort of
out of order.
interleaving that took place, right? So it looks like this does answer my previous question of is there actually interleaving taking place in the memory controller? So I guess the answer to that is yes, and I must have made a mistake in the DMA engine. So
right, so it's both interleaving and reordering. So yeah, I guess yeah, we need a much more complex DMA engine there in place.
No, I thought I handled this case. So the only thing about the AXI DMA module that's a little bit funny is that it always handles stuff in the transmit in the operation tables in order. So the PCI Express one, it has FIFOs to keep track of, you know, which entries are, you know, used and which ones aren't. In the AXI one, it basically turns the whole table into a FIFO. It just in terms of determining which ones are used and which ones are free. So if you hang on to one entry for a really long time, then once it's used up all the other entries, it'll wait until that entry is freed before it'll use it. So basically the idea is that PCI Express, you're going to get a lot of reordering. So we have to make sure that you can recycle stuff, ASAP. But for AXI, it's assumed that you're not going to get as much reordering. You might get some, but it's going to be pretty shallow. But it should still be able to handle reordering. So I must have made a mistake in there somewhere. I'll take a look though.
Oh, okay. Great.
Yeah, I mean, it's like if it wasn't going to handle reordering, then you wouldn't have an op table or whatever. It would be handled differently. But that's the whole point of those things, is to multiple in-flight operations and potentially some reordering and interleaving. So all that can be unwound.
Yeah. I suspect some of that's probably due to the deadlock considerations.
The deadlock considerations?
Yep. I mean, it's not just, so with PCI Express, you have to deal with the fact that you need to make sure that you clear responses before requests. Effectively, responses have higher priority.
Right.
Make sure you don't get deadlock. You've got a whole wad of requests but you're not able to progress with responses, so everything gets constipated. We have to deal with the same thing when we're mapping PCI Express to Rapid I/O. There's very specific rules for that, and I suspect that's what they've implemented on that. So it's not just the visibility and the prioritization is not just priorities, but it's also request response handling.
Well, in this case, we're actually talking about a Zinc device where we're just talking to the Zinc programmable software side, the hardcore side over AXI, where we're running into some issues. Nothing to do with PCI Express.
You're not dealing with raw TLPs.
Yeah, in this case, yeah, we're not. But for the other ones, I mean, the case that it works right now is PCI Express handling with raw TLPs, because yeah, you get all sorts of reordering and stuff that takes place there. Exactly where that's coming from, I'm assuming that's all on the chipset side. That's actually handling this stuff, the chipset memory controller, on the host side. But yeah, well, that's pretty standard.
The Xilinx hardcore does some weird stuff. I mean, there used to be tons of errata on it. We got bitten on it before, including things like, so we were seeing weird things that actually locked up our bridge. They would go out and put the data out on AXI before they put the address out. And on our AXI 4 light bridge, we had just assumed the address phase was going to occur before the data phase. And when we ran a sim with their hardcore, we're going like, oh, well, that's weird. So, and stuff like that.
Wait, so this is the actual PCI Express IP core, or this is their bridge IP, which uses a lot of soft IP?
Yeah, well, everything in Xilinx is, so the hardcore has this huge wrapper around it. And a lot of that's to deal with issues they had on the TLP interface. I mean, if you looked at the errata list, it was like, yikes.
For which device?
Zinc 7000.
Oh, okay, I see.
I thought we were talking about Zinc.
We're working on Zinc MPSoC.
Oh, you're talking about Zinc UltraScale, okay.
Yeah. I just been using Zinc kind of as a catch-all. I don't think we're running anything on the 7000 series right now.
Okay, never mind. They probably got it all clean.
Well, I guess they used the Zinc 7000 series to, work out the kinks for the MPSoC devices.
Could be. But we ran into a lot of problems with the PCI Express interface until we went and did some sims with their actual hardcore to see what was actually going on. And then we're going like, oh, well, that's weird. Because it would lock up the system, and it mean hard. I mean, power off the board. The debugger wouldn't work. Yeah, it was scary. And that was one of the things that was kind of concerning, you know, if you're talking about high availability, they clearly didn't have a timeout mechanism on their AXI interface, their AXI IT. So if it hung, it
Well,
just
I mean,
hung forever.
AXI doesn't really, oh, timeout. So if you issue an AXI operation, then it'll actually complete it at some point, even if the
Yep.
PCI Express packet gets dropped. I see. Okay.
Yep. And AXI spec talks about that, but it never says how you should do it. And ARM, you know, on their stuff, they don't have timeouts for most of the stuff because, you know, it's a cell phone, locks up, you just reset your phone. Seriously.
Yeah, I was under the impression that with AXI, you basically just have to reset the whole thing. You can't really do any kind of partial resets or anything just because of this kind of issue, right? If you reset a piece and there's an active transaction in there, then you're hosed, basically.
Well, no, they talk about it. They talk about timeouts in the AXI spec, but they don't give you any policy for implementing it. So everybody's sort of like it's the hot potato and nobody does it. That's my experience.
Interesting. I mean, it's like with AXI Lite, you know, what can you even do if something times out? You have no ID fields or anything to associate the responses with the original request. So.
Yeah, but you can propagate back to, for example, the PCI Express interface, and I don't remember, I'm pretty sure there's a mechanism on PCI Express for doing something equivalent to a bus error.
Well, right, yeah. So that makes sense. In that case, you're basically, you never time anything out on AXI necessarily, right? Everything has to be completed. But if the operation fails, you know, over PCI Express and the packet doesn't come back within a certain time, then yeah, you do need to actually properly terminate the AXI operation.
Right, so that's my point. You need to do it somewhere, detect it, and percolate the issue back.
Right.
Because there's no clear guidance in AXI as to how to do this and who needs to do it. Is it the nodes at the end that may be bridging over to another bus or another interface, like a DRP bridge? Then everybody just sort of goes, don't need to worry about that, and it just doesn't get handled.
Gotcha.
That's been my experience.
Well, I guess in the Zinc case, that just ended up being another errata.
Yeah.
I think the at least I hope their current bridge IP is better, but maybe not. I don't know.
I don't think so, actually.
Wishful thinking.
I haven't checked because we fixed all the issues and we haven't seen it since. So if there is a lockup for response timeout, what happens? I have no idea.
Well, especially in the case we are talking about the Sync AXI integration, so the PS system will definitely hang if the AXI transaction will never be answered. So
right.
At some point there should be a timeout mechanism on kind of the top layer of the FPGA interface.
And it gets even worse. The debugger hangs, the software on the host hangs.
I mean, I think what ends up happening is like the AXI interconnects hang. And then when that happens, you're hosed. Because everything goes through the interconnect.
Right, exactly. So somewhere that deadlock needs to be, you know, broken. There needs to be a timer somewhere. But once again, because there's no clear definition, should there be a timeout monitor in the AXI interconnect block? Or is it the endpoint's responsibility? Or is it the master's responsibility? And nobody winds up doing it.
I mean, I think the way the AXI protocol works is kind of has to be the endpoint's responsibility, unless you insert some sort of a firewall block or something, which I guess we're seeing in a lot of devices as well here and there between reset domains and stuff is blocks that will keep track of all the outstanding transactions and terminate them all if something gets reset. Otherwise, you know, you can't really recover.
Well, the interconnect could do it as well. And the host.
Yeah, I suppose the interconnect could do it. I don't know if I don't know if the initiating master could do it, because then you'd have to like inform the interconnect that, yeah, this thing timed out. And I don't think there isn't a standard way of doing that. So
Well,
I think
that's the problem.
yeah.
There's no standard way of doing it at all, so everybody just sort of
Yeah.
avoids the issue because it's ugly.
Right. Well, what are you going to do?
Yeah.
Besides get some more white hair, you know?
Yeah, there you go.
All right. Well, I'll take a look at the at my AXI DMA and try and figure out what happened. I guess this was in the read direction, I think, right? Yeah. All right. I'll take a look at that and see if I can figure out what's going on with that. Anything else? Anything else to report?
Nope, just if you need some more input on this one, I don't know, then just ping us and you get more. I don't know
Sure.
if Toby actually committed all the code. I guess so. Yeah, it was the original code. There's just a little reset fix that will be provided later on anyway.
Okay.
So somewhere was a signal missing in the reset, which
Oh,
hangs up
okay.
Corundum when, well, you need to reset this signal.
This is in the DMA or?
Not sure anymore.
Okay. Well, we
We'll
should
provide
probably
a PR for it.
get that added. Yeah, that's probably more important in the short term. Yeah. Oh, do you guys have anything to report on the DPDK driver you guys have been working on? I know there was a couple of questions about that in terms of you're running into some issues on the DPDK side, but anything new? Is everything working?
No, not working yet.
Okay.
I guess they're currently fighting IOMMU issues. And because I guess we have a little special setup here on our end, but we'll see. I guess we will get through this as well. And we had some discussions with customers about what they want to have implemented and such. So we got a little bit distracted on this side as well.
So these are different projects, or?
Yeah, they're
customers
loosely connected, let's say.
I see. Okay. Fair enough. All right. Well, if we have nothing else to discuss, then I guess we can adjourn for this session. Anything else? Going once, going twice. All right. Well, I guess we can close this down, and we'll see all you guys in 2 weeks. Thanks for tuning in. It's been a good discussion.
Thanks, everyone.
Thanks, gentlemen.
Thanks, everybody.
All right. Talk to you.
Bye.